During our study of medieval natural philosophy, we spent a lecture looking at alchemy, and now it's time to return to that topic just a little later on in time, down in the 16th and 17th centuries. In this lecture, we're going to look at several of the developments that characterized alchemy, or chemistry if you prefer, in this time period. But before I go any further, I should say something about terminology. In the Middle Ages, the topic was almost always referred to as alchemy. The prefix al, the Arabic definite article, signifying the origins of alchemy in the Arabic world. But over time, this article began to disappear, and so we get the word chemia from alchemia, and thus our word chemistry. Undoubtedly, part of this had to do with the philology of the humanists of the Renaissance, trying to purge out these intrusions, these Arabisms that they felt were polluting, in their idea, the purity of the Greek words. So we have this odd situation that the words alchemy and chemistry were used simultaneously in the 16th and 17th century, and for the most part interchangeably. Now, the differences that we recognize between the two words is actually a development that comes from about the end of the time period this course is going to cover, the decades around 1700. Well, when last we looked at alchemy, chemistry, I emphasized the many pursuits and topics that were encompassed under this heading, from matter theory, pharmaceutical preparations, all kinds of different things, technological processes, material productions. These all continued down into the 17th century, and some of them at least on into the 18th. What I'm going to look at first, then, is matter theory. Well, in the Middle Ages, the general matter theory of the alchemists was the dyad, that is, the mercury-sulfur theory of the metals, that all metals were composed of two substances, one called mercury, one called sulfur. This was joined, as I mentioned a few lectures ago, by the Paracelsian triad. Paracelsus, remember that person who's this iconoclastic, bombastic character who's very interested in chemical medicine, among other things, adds a third principle, mercury, sulfur, and salt, he says, and this produces an earthly analogy, so to speak, to the heavenly trinity of Father, Son, and Holy Ghost. Everything, according to Paracelsus, not just the metals, has its mercury, its sulfur, and his salt. Now, Paracelsus was not necessarily terribly consistent about these kind of ideas. He wasn't terribly consistent about very many things, but his followers, at least, tried to make these ideas more consistent. And so they developed this theory of the triad, sometimes called the tria prima, meaning the three first things, the three primary ingredients of everything. So it's sort of an elemental theory. In the course of time, in the late 16th, most particularly in the early 17th century, this triad was expanded to a pentad, that is five principles. So mercury, sulfur, salt, and then earth and phlegm. So that's another one. We've also seen in an earlier lecture the water theory of Van Helmont, where he says everything is basically water, that reprise of the Thales doctrine that everything is water. The water, organized by the action of semina, of seeds, produces everything that we see. And there's still the old Aristotelian quaternary, the four elements, the four Empedoclean elements, fire, air, earth, and water. And all of these are coexisting. Don't think about this as being some kind of linear progression from one kind of matter theory, one kind of elemental system to another. They're all mixed together in there. In the middle of the 17th century, you could find adherents of any one of these several possibilities. And they were chosen by a particular practitioner because they accorded better or more congruently to the kinds of things he was interested in. The pentad, for example, was particularly useful for people who did a lot of distillations for medical preparations, because if you take any plant or animal material, put it into a retort and destructively distill it, you'll get off roughly 5 different kinds of substances. You'll distill off a watery substance, that's the phlegm. You'll usually distill off something that's got a strong odor and is volatile. That's the mercury. You've also get something, an oil, something oily, deeply colored, smelly, usually inflammable. That's the sulfur. If you take what's left in the retort that doesn't distill and put it in a fire and heat it up quite hot so that it's just ashes, and then leach those ashes with water, the water will extract a salt. There's the fourth one. And then there'll be some of the ashes left over that are insipid and insoluble, and there's your earth. So these responded to the needs, they responded to the practices of the various chemists. I should say, just in passing, that this array of theoretical systems is actually characteristic of the 17th century. We've seen this before in other venues, the numbers of different ways, the methods of dealing with the natural world. Let me also say something about particulate matter theory. We looked in the Middle Ages at the particulate matter theory of Geber, and we've looked in a previous lecture at the revival of ancient atomism by Gassendi and others. And I mentioned then that these two traditions joined together. The chemists provided very important proofs for particulate matter theories. Their experiments seem to be the best at explaining these. For example, if you take some silver, dissolve it in aquaphor, today we'd call it nitric acid, we get a clear solution. You can filter it, it passes through the pores of filter paper. You can take that clear solution, throw in salt, and all of a sudden a heavy white precipitate will fall out as an extremely fine powder. You can take that powder, put it in a fire, in a crucible with a little bit of charcoal, heat it up, and you'll get your original silver back. Which means that your silver, when it dissolved into a transparent fluid, must have been dissolved into such tiny particles that it could pass through the pores of the filter paper without being destroyed in its identity. So that's an important argument in favor of the permanence and the minute particle size of corpuscles, of atoms, whatever you want to call them. We can't really talk about chemistry in the 17th century without talking about Robert Boyle a little bit more. We've mentioned his corpuscularian system, but his accomplishments in chemistry are particularly important. He argued quite strenuously for the importance of chemistry to show and to illustrate ideas from the mechanical philosophy, for example, to argue for theories in natural philosophy. He said it's not just for making medicines or for trying to produce gold. It can also give us an important key into the natural world. So he devoted special attention to chemistry. In fact, he got into, at least by his own account, he got into a bit of criticism for doing so, because chemistry did not have a high status, a high intellectual status at the time. It was embroiled with the problems of fraudulent people who would hire themselves out with promises of making gold, which were ultimately unsuccessful. So Boyle, in his early days, when turning to chemistry, actually had to confront this bad image of chemistry. We'll come back to that in a moment. For Boyle, everything was made up of the same universal Catholic matter. That's his term for it. And this universal Catholic matter comes in different shapes and sizes, or rather is particularized into different shapes and sizes, and that gives us different properties. Quicksilver, a very mobile liquid, is made up of little spheres that can roll on each other. Whereas oil that's thick, Boyle says its corpuscles are like eels that are long and thin or branched, and so they stick together. Boyle's great foes were the Aristotelians with their ideas of substantial form, that in a chemical change, one substantial form is destroyed and another one is created. He borrows some ideas from earlier chemists, saying that this just doesn't make sense in a lot of ways. Remember the silver experiment I told you. It seems unlikely that you could start with silver, with the substantial form of silver, make it into a fluid, then into a white powder, and then get the silver back again, as if the first substantial form came back just as it was originally. That seemed unlikely to him. Boyle gets a lot of inspiration from Van Helmont. In fact, he repeats Van Helmont's willow tree experiment Not for 5 years, but instead using peppermint. He takes a sprig of peppermint and puts it in water, and it roots and it grows, and he can distill peppermint oil out of it, but the only thing this peppermint sprig has been feeding on is water. So it seems to validate Helmont's water theory. Boyle has some reservations about it, but more or less, he's certainly very, very influenced by Helmont. Notice that Boyle's concept rules out the possibility of distinct elements. And this is one argument of his very famous work, published in 1661, The Skeptical Chemist. If everything is made of one single matter and differenced only by the shape, the size, and the motion of the particles, then we can make anything out of anything. We can turn anything into anything because it's all the same matter. It's all the same stuff. It's just the shape that changes. So Boyle's idea actually further undergirds the possibility of metallic transmutation. This is a little bit ironic because in many historical accounts, Boyle's Skeptical Chemist is read as a refutation of transmutational alchemy. It's not that at all. Boyle was actually deeply interested in traditional alchemy. I'll come back and talk about that in a few moments. Various mechanical corpuscular systems were devised, but many of them seemed quite contrived and were not convincing to some people. One person by the name of Nicolas Lemery, a Frenchman who was working in the latter half of the 17th century, talked about acid particles being pointy, and so that's why they taste sour, because they prick our tongue. Alkalis being fluffy and sponge-like, and so the two, alkali and acid, neutralize each other when the points of the acid get stuck into these spongy alkali particles, and we get not a sour or a bitter thing as the result. Well, I just mentioned alchemy briefly. Let me say some more about transmutational endeavors. The search for the philosopher's stone, that substance which is the means of metallic transmutation, was still very widely pursued in the 17th century. In fact, the 17th century is the great flowering point of transmutational alchemy. There are more books published on that topic in the 17th century than in all the previous centuries combined, probably. Royal and princely courts almost always had their court alchemists. This would be a person who would promise, who would think he would be able to make gold or silver from cheaper metals, would be hired for a fee at a salary, be patronized, that is, by a prince or a count, a duke, an emperor, and live at court and work on this problem. Some of them undoubtedly were sincere in their belief that they could actually solve the problem of transmutation. That's for certain. Others were almost certainly intentional frauds, that is, intentional con men, and many of them ended up in the gallows. The last time we talked about alchemy, I mentioned the rise of secrecy and metaphorical language in the 15th century in alchemical treatises dealing with transmutation. This remains at a high level throughout the 17th century. In fact, if anything, it gets even more complicated with iconographic images, emblematic images. We've talked about the emblematic worldview, where things are not only things, they're emblems, metaphors for other things. This is probably a related phenomenon. Alchemists enjoyed playing sort of a game, sort of a hunt for the answer in their books by writing in a studied, metaphorical, riddling kind of way. Let me give you one example of a very, very interesting character. His name is George Starkey. He's almost exactly the same age as Boyle. He's born in 1628, except that he's born in Bermuda. And he dies in 1665 in the Great Plague of London. Interesting character. Leaves Bermuda, goes to the Massachusetts Bay Colony, gets a degree at Harvard, which is founded by this point, graduates in the Harvard class of 1646, begins practicing medicine, and then emigrates to England, where he becomes an associate of Boyle and other important people at the end of the 17th century. Now, Starkey was a very keen experimentalist, an experimental worker. But one of the reasons people were interested in him is that he told a story of how he met a successful transmuter of metals, an adept, by the name of Irenaeus Philalethes, which means the peaceful lover of truth. This Philalethes is a person he supposedly met in America who showed him transmutation, gave him a small portion of the Philosopher's Stone that could transmute to silver, although didn't tell him the whole secret. We now know that, well, first I should say, he also circulated some manuscripts which were supposedly lent to him by Philalethes, and these were eventually published later in the century, at most of them after his death, and they became extraordinarily popular works, extraordinarily popular. What we now know is that Philalethes was the creation of Starkey. It was a pen name for him, and he made up this story. But you shouldn't think about him as being a liar or a con man. He was anything but, because this sort of Starkey-Philalethes split exemplifies the split between practical work in the laboratory and the public face of transmutational alchemy. If we look at one particular example out of these works, and that is Starkey thought in about 1650 he had produced a material that was the correct starting material for the Philosopher's Stone. A description of this shows up in the Philalethes tracts, where it's described in terms of the interactions between a fiery dragon and a magnet, and rabid dogs that are drowned in a pool of water, and the doves of Diana, and hermaphrodites, and all kinds of lurid, metaphorical imagery. On the other hand, just after he discovered this, he wrote a letter to his new friend Robert Boyle, in which he describes the same process, except he says here, take 9 parts of antimony and 4 parts of iron and mix them in a crucible of such and so size and add saltpeter to the amount of 2 ounces. Very precise operational terms that anyone could follow. So there's a public and a private face. There's a private face where these people are working in their laboratories diligently, with their eyes open, knowing what they're doing, able to describe what they're doing in precise operational terms, and there's a public face as well, which is full of secrecy. We have to remember both of these two sides of it. Boyle himself was a very keen searcher for the Philosopher's Stone. After he got this recipe from Starkey, he actually worked with this recipe for more than 40 years. And at the end of his life, when he was writing up his will, and he was listing some of the most precious items he owned to make sure they were properly disposed of upon his death. There's a little scrap of paper that survives among his archive. This very process, this animated mercury, is listed there 40 years later. Well, what other sorts of things were going on in chemistry at this time? Another big search, besides the search for the Philosopher's Stone, was the search for something that Van Helmont referred to as the alkahest. The alkahest was the universal dissolvent. Now, by calling it the universal dissolvent, that diminishes its real importance for Van Helmont. What it can do is you take any substance, put it into this, and it would divide it into its initial ingredients. Upon further, so it's an analytical solvent, it divides things into what they're made up of, and then upon further digestion it would reduce anything back into its primordial water by mortifying, as he says, the seeds that made the water be something else. This was something that both Boyle and Starkey were very interested in. Boyle was certainly interested in it because it would help him chemically talk about the materials that things were made of, what stuff made up of. You have an analytical solvent that can help you answer that question. Of course, Van Helmont was very secretive about how this is prepared. He only gives hints, and both Starkey, Boyle, and dozens of other people spend a long time trying to find out how to prepare this substance. All right. Well, let's now move on to another subject within chemistry. I mentioned earlier in this lecture that chemistry had a low professional status. It was not part of university education. It was often practiced by people that had a low social status in the sense that they were working with their hands. They were getting their hands dirty with empirical practice, dirty with coals. They worked with stinky stuff like chemists still do. And there wasn't a classical tradition of chemistry, like there's a classical tradition of astronomy or of physics. What did develop in this time period through the 17th century is an enhanced status for chemistry and an enhanced professionalization. First of all, its professionalization has to come about through some kind of pedagogical reform. It has to be taught. Chemistry, as I say, was not at the university as part of the standard curriculum, but over the course of the 17th century, more and more chemical textbooks started appearing. One of the important people starting this tradition is Andreas Libavius, who's born in 1540, dies in 1616. He's a Saxon, he's a pedagogue, he runs a gymnasium, and what he does is he imports things like humanist taste and a desire for pedagogical utility. So this kind of humanist philology, the idea of active civil life, of pedagogy, into the chemical tradition. And he writes an enormous, massive textbook trying to organize the preparative processes and some of the theories of chemistry. An immense work called Alchemia, or just simply Alchemy. He assailed secrecy and he stressed preparative utility. Well, the first university post in a chemical field was actually founded in 1609 at the newly founded University of Marburg, Germany. The position was filled by one Johannes Hartmann, but by calling him the first professor of chemistry, we're being a bit inaccurate. What he was really hired to do was pharmacy, chemical pharmacy. And this is one of the very important roles of chemistry in the 16th and 17th century. It's what Paracelsus stressed. He stressed that God has produced a world that has all these medicines in it, but many of these medicines are corrupted the same way the world is corrupted by the fall of man, and these corruptions come in the form of toxins and poisons. Therefore, what we need to do is to use chemistry to purify all these substances from their toxic admixtures. So we use chemistry, this idea of Scheidung, separation, that Paracelsus promoted, to purify substances, to extract their medicinal essences, to make things wholesome so that they're not dangerous anymore. And that is a predominant part of chemistry throughout the 16th and the 17th, late 16th and the 17th century. You might note, for example, that in Britain, if you meet a chemist, that's a pharmacist. So that usage, still retained in British English, is testimony to this close linkage of pharmacy with chemistry. People like Libavius initiated an important series of textbooks which were published throughout the century. Often these accompanied lectures that were given in various places, in various schools, in various centers. One of the important centers was in Paris at the Jardin des Plantes. This was a herbal garden. It still exists. If you go to Paris, there's still a herb garden connected to the Natural History Museum. So it continues. It's a Crown-funded garden of medicinal plants. And very interestingly, it was one of the important places in Europe where new plants from Asia, from the New World were sent and were grown there, and then their medicinal utility was studied. There was a professorship of chemistry set up in relationship to the plant garden. And it was filled by a number of important people who later put their lectures into written form, printed textbooks, or wrote textbooks to go along with their lectures. Part of the problem with these textbooks, though, is that naturally enough, for courses that were based on medicinal plants and pharmacy, they tended to stress medicinal preparations. They had recipes galore in them. They tended to teach basic operations of chemistry like distillation, crystallization, sublimation, but generally minimal theory. The theory that they did have tended to be Paracelsian, primarily, working with the triad, or more often the pentad, the 5 elements system. And they stressed the utility of chemistry to medicine. Now, this was a problem to some people, like Boyle. Boyle assailed them because he thought they didn't pay enough attention to theory. That chemical theory was so important, and the application of chemistry to elucidating the secrets of natural philosophy was just as important, if not more important, than these practical processes. Well, what about the status of chemistry? Well, as more and more textbooks start being written, chemistry gets a larger and larger share of attention. But professionalization is really what helps chemistry the most. One of the important moments for this is the foundation of the Royal Academy of Sciences in Paris. We're going to talk about scientific societies in a later lecture, but for now, let me say that this institution, crown-funded institution, was founded by Louis XIV, gave a particular institutional home to chemistry because there were positions, paid positions for people to study chemistry, to study pharmaceutical preparations, but also more theoretical chemistry at this academy in the late 17th century and through the 18th century. It's probably no coincidence that one of the most important characters in the history of chemistry, Antoine Laurent Lavoisier, comes out of this same Royal Academy of Sciences. That's much later. That's in the latter half of the 18th century, though. A curious thing has to happen here, though, in the professionalization. I mentioned at the outset of this lecture the two words alchemy and chemistry, how they were used largely interchangeably. Well, they're not interchangeable anymore. How did that come about? Well, there are a lot of reasons. I don't have time to go through all of the reasons, but one of them seems to be the disillusionment with the goals of transmutation. That is, chemistry had gotten a bit of a bad name from the frauds that were perpetrated in its name. So people trying to make a buck, claiming to be able to know transmutation, and not necessarily being really serious about it. With professionalization comes a need to purify the field in a sense. That is, to get it away from bad associations. And it is really this Royal Academy in Paris as one of several places where the word alchemy, where the practice of the transmutation of metals gets shunted to the side as being less important, as being not important. That's at least the public face of it. There's a public attempt to say, oh, well, we're now chemists. We're not doing that thing, that transmutation thing that's more closely affiliated, rightly or wrongly, with cheating practices, fraudulent practices. That's at least the public face. As it turns out, a lot of people at this time are still working on the problem of the transmutation of metals because there is no theory that tells you that transmutation can't happen. So clearly, there is still a theoretical foundation for it. So this is one of these interesting social phenomena where definitions, boundaries are set up within the sciences for specific social goals. In this case, elevating the status of the chemist practitioner. There was also an attempt on the parts of some people, Boyle I've mentioned as one, to get chemistry away from the practical processes of pharmacy. That takes a great deal longer. It turns out that it's not until the middle of the 18th century, maybe even a little bit later, that chemistry in the universities becomes something that's no longer necessarily related to pharmacy. That connection, chemistry, medicine, pharmacy, is of very, very long duration because chemistry is just so darned useful in isolating substances, in purifying substances, and talking about material substances. Fine. Well, The issue of chemistry, the issue of alchemy in this period is very complex. Again, like the rest of the 17th century, lots of things are going on. For now, however, we're going to conclude on this topic and go to look at one of the 17th, early 18th century's most well-known characters, and that is Sir Isaac Newton.